I am muted. Now I'm unmuted. Okay. So, let's begin. So I guess the question is like, what's the point of me doing this little video? I think I just want to kind of go over some stuff on the final and just kind of, you know, talk about it a little bit. And I'll leave it up so that, obviously people who are missing it right now can come back at a later time and watch it. Okay. So, let's look at some of the problems. So, yeah, let's look at the induction problem first. I guess the question is, is there anything that I should say about the induction problem? I don't know. Yeah, you can submit as many times as you want. I think I have it set to unlimited submissions, so you're cool to submit as many times as you want. So, okay. So basically, remember, induction is basically all about a base case and then an inductive hypothesis. So let's say that the base case, is I guess n is equal to 1 in this case. And then you would basically say, well, when n is equal to 1, you'd have 1 times 2 divided by 2. That's 1 quantity squared, so that's good. And, well, I like PDFs. They make it a little bit easier for me, but it's okay. And then the whole point is that the inductive hypothesis is that we want to assume, right, that the sum from k equals 1 to n is equal of k cubed is equal to let's see, n times n plus 1 right squared. We want to assume this, and so let me just compile the LaTeX and then you can see what I'm talking about. Where is it? Here it is. Let's hope it compiles properly. There we go. So we assume this, and then we want to show that this is true when you replace it with k with n plus 1, right? You want to show that this is true, and then of course you need to replace n plus 1 here and n plus 2 here. So this is, so you want to show this next line. So there's a bunch of different ways to do it. I think one of the easier ways to do it is probably to, the thing is, in the end, it's a bunch of algebra, right? Because you're going to have to end up doing like an n plus 1 cubed plus some term, and you're going to have to try to get that equal to the right-hand side. So let me just do an example using the k squared instead of k cubed. So for instance here, let's try to prove, instead of the k cubed case, let's try to prove the k squared case. So when you sum up all the squares, you're going to get, if I'm not mistaken, if I remember correctly, you're going to get n times n plus 1 times 2n plus 1 divided by 6. I think that's what you get. So I'm claiming this. Right, so I'm not doing the I'm not doing the cube example anymore. I'm just doing the squares example. And so let's try to prove the base case. So what's the base case? The base case should be the same thing, is n is equal to 1. So what we're going to do is we're going to plug in 1, and I think what we're going to get is the fraction of 1 times 2 times, okay, 2 times 1 plus 1 is 3, so that's 1 times 2 times 3 divided by 6, which is equal to 1. So that's right. And then what do? Right? Then what we do is we try to show it for the next one. So we say, assume it's true up to n, and then we want to show it for n plus 1. And of course, yeah, so we have to look at what the formula for n plus 1 looks like. And so what it looks like is it's going to be n plus 1 times n plus 2 times what? 2n plus 3 divided by 6. And so that one is actually a bit complicated, right? Because if you want to show something like this, one way to do it is actually just to FOIL the whole thing out. Because what you're going to do is you use the inductive hypothesis to say that, well, what do we say? We say that if you go up to n plus 1 of k squared, that's the same thing as going to n of k squared, and then just adding on n plus 1 squared. And then by the inductive hypothesis, right, this is the place where we use the inductive hypothesis, that's equal to the sum from, well, okay, oh, no, I'm sorry, that's not equal to the sum. That's equal to the fraction of n times n plus 1 to n plus 1 over 6, like this. So let me just show that. So we use the inductive hypothesis to say that, so this is not the inductive hypothesis here. This is just the definition, right? This is saying I'm going to pull off a term, and then I'm going to write the term separately. This is the inductive hypothesis here, that this part here is equal to this part. And I actually haven't written the full term in yet. I need to put in the n plus 1 squared in there. And then you might actually be thinking to yourself, like, this might actually be pretty hard, just like the other one might be pretty hard if you're not used to doing the factorization that way. It might be pretty hard to factor it back out. One thing you can always do is you can say that if you wanted to do the algebra by factoring, you can say that this thing is equal to, let's see, n plus 1 times the, fraction of n times 2n plus 1 divided by 6 plus n plus 1. Like this. So you can say something like this, and this actually works by analogy. So this works by analogy. You can do this kind of operation here. So what did I do here, right? I factored out one of the n plus 1s out of this term, and I factored out the n plus 1 out of this term, and then I just have to combine these things. And so to combine them, I need to make this 6n plus 6, I guess. And then I need to square the top. So what we're going to end up with is that this thing is equal to what? It's going to be equal to n plus 1 times the fraction of, what is it? 2n squared plus n. And that's all divided by 6, but then we're going to add on another 6n plus 6 because we're making like denominators. So I'm going to do something along the lines of this. And then I can just factor. So I'm going to have to, so I need to combine everything together. So I combine everything together and I get, well, what do I mean by combine? I mean that I get 7n plus 6, and then I have to think of how to factor that. And that one's a little bit difficult to factor, but hopefully I can cheat, right? Because I know it has to be n plus 2 times 2n plus 3, and so I just check that, right? I say, is n, n times 2n, that gives me 2n squared? Yep. 2 times 3, that gives me 6. And then the odd term, n times 3 gives me 3n, 2 times 2n gives me 4n, so 7n total. So that works. So I can factor this thing back out into, I can factor that thing back into, and I'm sure most of you have done the algebra already for the other one. It's actually, I think the other one's actually a little bit easier than this one. This one's a smaller degree, but it's actually a little bit harder in terms of the algebra. But And that's just how life is sometimes. And so there you go. You get n plus 1 times n plus 2 times 2n plus 3, all divided by 6, which is the formula we wanted to prove. So I think that's... I didn't want to say too much about number 1, but I've said quite a lot about number 1. I kind of wanted to go over induction again too, just to be clear, because I can never do enough induction. Okay, and so now that I've spent 10 minutes on that, let's get to the thing everybody cares about. So number 2, I might actually transition out of LaTeX and just do it using some drawings. So let's look at what I think this is probably why I want to do it this way. I just want to draw something out and show you guys what I mean. So for number 2, we want to show that, let me see here. What do we want to show? I don't know what we want to show. Hang on. I wouldn't do a square root of both sides. You know, I would do it the way, so the way I did it is okay. Let me just cut and paste this induction problem. So, you know, I wrote this down and I thought to myself, I'm going to definitely draw them a picture, right? Never actually drew you guys a picture, so let me draw you that picture now, and hopefully it helps you. And if you haven't solved the problem already, or if you've solved it, but you're kind of still confused about what the heck is going on, let me show you what I mean by all of this. So if you remember that this thing is a B0, whoa, that's 75 point font. Let's make it 25 point font. That's better. So that's a B0, it's a single node, right? Now you don't know anything about that, right? Not really. A B1 is the same thing as a B0 with another B0 attached. Like that. A B2. Oh, no. Give me this. So what's a B2? Right? A B2 is the same thing as a B1, except you have another B1 attached. And then I'll draw a B3, and then we'll talk about the n's and k's. And once we talk about the n's and k's, then we will talk a little bit about the induction. So, okay. I think that's almost, I want this to be kind of good looking, because we're about to use it for B3 and B4 possibly. So let's make this decent enough looking to be passable. Okay, so that's a B2. And let's make one more. Let's make a B3. So B3 is a B2 with another B2 as a child. Like that. And I don't know if that's very good. Let's shift that one up just a little bit. There we go. It didn't quite work. Okay. So, there we are. All right, so that's a B3. So now we have to talk about, okay, that's still 75 point font. Change to 20. All right, cool. So now we have to talk about all the levels and the K's and the N's. So basically, what should I say? The number, so this is level 0, okay? Oh my goodness, please stop doing that. Right, so this is level K equals 0 here. So everything on the top is level K0. And then the next level is level K1. So let me try to draw that. So everything down here is level K equals 1. And then we have another one, which is here, which is level k equals 2. And then finally we have another one, which is k equals 3. So I wanted you to prove that the number of nodes at the k level in a Bn is n choose k. And so let me show you why that's true. If you have, so what is n choose k, right? What is n choose k, right? It's the number of ways to pick out of a box of n things where we pick k things. So let's shrink this down. So it's the number of ways to pick out of a box of n things where you pick k things and then the letter a. Okay, so if you have 0 things, how many ways can you pick 0? That's a little hard because, as it turns out, it's not something that makes sense to us really. But on the other hand, I will say that the good news is that 0 choose 0 is just equal to 1. And the reason why it's equal to 1 is because you might have to write out all the factorials and stuff, but they all cancel, and the thing is eventually equal to 1. Let's see if it actually renders or if it just crashes. Oh, it actually might have rendered. See? Oh, it did it wrong, but it did render. It did it wrong, but it did render. Okay. Let's try it again. Here we are. So 0 choose 0 is 1, and I'm not going to go into all the details of the math that is required to get there, but I mean 0 choose 0 is 1. We're just going to assume that, and that's our base case, right? And so the point is that it's really hard to draw a Bn, so all you have to really do is think about it this way, okay? Let's say you take a B3, and now you're going to make a B4. Right? This is the hint that I want to give everybody about this problem. So in the inductive step, you might be thinking, I really don't understand how to do all of this. But the good news is that if you're at, let's put this all the way down. Oh, I need to put it under everything. I guess my bubbles are not straight. Okay. I've learned a lesson. We've all learned a lesson today, which is that they were a bit more askew than I thought they were. Okay, so if we look at the different levels, and I've kind of drawn in the different levels here. Yeah, I can even make them colored. So the k equals 1 level, right? So at this level, what do we have, right? Pretend that this is not a B3. Pretend that this is a Bn, right? So instead of being 3 nodes here, how many nodes is this thing going to have? Well, it's actually going to have n nodes plus 1, right? At this level, right? Because basically we're pretending that this is 3 choose, or we're pretending that this is n choose 1, and n choose 1 is just equal to n. And then at the next level, basically, what do we see? We see that at level 1, we have, I guess this is the way I really want to say it. This is the real hint. So at level 1 of a Bn plus 1, what do we have? We have a Bn. We have the root node, and we have n other nodes, right? And then let's look at some other. I don't know how to change the default font. I really don't want that to be 75 all the time. So let's look at some other levels. And so the next level here, it's a little bit harder to think about, but here, basically this would be n choose 1 layer, and this would be n choose 2, right? So technically 3 choose 1 and 3 choose 2 are the same thing, which is why it's both 3, but in some other cases it will be different. So in that case, basically here what we're going to have is we're going to have n choose 1 plus n choose 2, right? That's what we're going to have. So let me try to draw that in. N choose 1 plus n choose 2, which, as it turns out, is equal by the formula to n plus 1 choose 2. So here we have n choose 1 plus n choose 2 is equal to n plus 1 choose 2. And so that's how many nodes are going to be in here. Now I know you're just like, well, this is 3, but you have to pretend that this is n plus 1, or n choose 1, because this is the level here, and the level here is n choose 2, and the reason why is because this one is shifted down by 1, right? So that's the trick here, is that this bn gets shifted down by 1 level. Right? So that's kind of the trick to this problem here. And so basically if we just keep going, what we'd end up seeing is that the next level would be like n choose 2 plus n choose 3, which would be then n plus 1 choose 3, right? So that would be the next level. And then the next level would be what? So, well, it'd be n choose 3 plus n choose 4 is n plus 1 choose 4. You don't have to prove this formula, right? You just have to do the counting of the nodes and argue by the inductive hypothesis that this is correct. So what about the last level? So the last level is actually something like this. It's actually n choose n plus n choose n plus 1, which is going to be n plus 1 choose n plus 1, which is 1. But the question is why, right? And so the answer is how many ways, right? Remember what the symbol n choose k is. So here, like, what is the number of ways that you can pick n plus 1 objects out of a bucket with n objects in it, right? So I give you n things total, but I tell you that you have to pick up n plus 1 things. And so you say, well, that's impossible. And I say, I agree. And then I ask you, if you have a bucket of n things, and I ask you to choose n things, how many ways can you do it? Well, that's 1. So 1 plus impossible. Impossible here is just 0, right? If I say do an impossible choosing task, that'll just be defined as 0. It usually is defined as 0. Some extended coefficients exist, but let's not worry about those. The point is that n choose n plus 1 means out of a box of n objects, I'm going to pick n plus 1 objects. That shouldn't be able to be true, so we just define that to be 0. And then this one, n choose n is 1, and n plus 1 choose n plus 1 is 1. So basically that's how you do this kind of thing. And then you would say, like, okay, well, I agree for that for a B3, but what if I had a B4? Would it be the same way? And so let me draw out the B4 case for you. So this is a B3 now. N is the height of the, it's the, like, index of the Bn tree, right? Like, this thing, so this thing is a B3, I think. Oh, no, I'm sorry, this thing is a B4. This thing I'm about to draw is a B5, right? So this thing I'm about to draw is a B5. Which is a great show that no one knows about. Babylon 5. But anyway, so the point is that this B5 tree, if we look at the thing, it's going to follow the same property, except it's going to be a little bit different than adding two B3s together to get a B4. Because here, when we add the two B4s together, things are a little bit different. Right here, you have 4 nodes in the first B4, and then you have 1 node, so that makes 5 total, so that's fine. Right? That's 5 choose 1, so that's good. And then the question is, what is 5 choose 2? 5 choose 2 is equal to 5 times 4 divided by 2. You know, you can use a calculator for it, or you can, I don't really care how you find it out, but 5 times 4 divided by 2 is equal to 10, so we count them 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, so that's correct. And then what is the next one? So I think 5 choose 3 should also be 10. And you notice here it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then down here we say, what is 5 choose 4? 5 choose 4 is 5 again. And there we go. And then finally 5 choose 5 is 1. So as it turns out that, you know, this works. And so the question is, why does it work? And the answer is, well, if we assume that this thing at level 2 is 5 choose 2, which it is, 5 choose 2 is 6, and then over here, oh, I'm sorry, 4 choose 2, I'm sorry, 4 choose 2 is 6. So we assume that this thing is 4 choose 2, which it is, and then we assume that this thing is 4 choose 1, which it is, then we add 4 choose 2 plus 4 choose 1 and get 4 plus 1, so 5 choose 2. Right, and so that's how this works, right? So basically we assume that this first half has, what is it, 5 choose 2 nodes at level 2, and then we assume that the second half has 5 choose 1 nodes at level 2, because remember, we're shifting it down by 1 level, so instead of being at 5 choose 2 level, it's at 5 choose 1 level, or I'm sorry, I keep doing that. It's actually 4, right, because we're making the B5 out of 2 B4s. So, and then what we say is, because of that, 4 choose 2, let me just write it in like, you know, silly notation. Right, and so that's the equation that I've given you up top, that C42 plus C41 is equal to C52. And so that's basically the equation that you needed to use. And anyway, yeah, so that's basically how the induction works. You just kind of, you know, I'm showing it explicitly. That's what I really wanted to do. I didn't want to give you the whole answer, but I did want to actually like write out a few cases and literally just show you, like, if you have 2 B5s like this, you know, and of course this is going to be real big, but whatever, you know, it doesn't matter. So here it is, and I think it's aligned, it's sort of aligned, and now you can even tell more that it's ascending. The levels are definitely ascending in this direction, but whatever. So let's make this B6. And so this is a B6 once I connect it all. And then you would basically say here, well, at the 0 level, 6 choose 0 is 1. Cool. 6 choose 1 is 1, 2, 3, 4, 5, 6. So that's correct, right? And then 6 choose 2 is whatever it is. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, whoops, that's 9, whatever, 10, 11, 12, 13, 14, 15. And so is it 15? And the answer is that 6 choose 2 is 6 times 5 divided by 2, so that's 15. So that's correct, right? So that's basically what this problem is asking you to prove. And so yeah, you gotta kind of, I think the right answer in terms of like, if you want to draw a picture about this, is just pick something between, probably don't, maybe do a B5, do something between a B2 and a B5. I wouldn't say draw out a B6, at least not by hand. You see that they get a little bit complicated, right? So I wouldn't draw out a B6 if I could avoid it. I get the analogy, right? So the point is you're going to be arguing by analogy. You're like, I drew out a B3 for you, but really this is just a Bn, right? And pretend that instead of having 3 nodes, at the second level, it actually just has n nodes n choose 1 nodes at the second level. So that's how to attack this problem. I think that's as much hinting as I want to do for this. Yeah. So keep in mind that there are shifts of this identity. So for instance, there are other identities that are similar to it. So for instance, there's an n choose k minus 1 plus n choose k is equal to n plus 1 choose, not n plus 1 choose k plus 1, but n plus 1 choose k now. Let me show you that identity. And that one is actually, it's actually the same thing. So these two are actually the same identity. The only difference between them, oh, it's not equal to 1. I'm sorry, that was left over. It is not equal to 1. But, so this identity is also true, and so some people might find this one more useful, because if you're actually looking at the k level, then it would be k nodes and then k minus 1 nodes. If you when you figure it out, you'll understand what I mean by that. And let me just replace this identity with this. So this might actually be the more useful one. When I wrote it down, I just thought to myself, like, which way does it go? And I was like, oh right, it's n choose k plus n choose k plus 1 is then n plus 1 choose k plus 1. So, I just kind of remembered it and wrote it down. I didn't think about what exact shift I needed to apply to it to make it like perfect for the problem, which I probably should have done. Okay, so I think that's good for number 2. I think hopefully number 2 makes a little bit more sense now, and you can kind of attack it. I do kind of like the B6. Look at this thing. It's a beautiful little structure, right? I think I know my answer to number 12. So let's go back to the document. Let me look at this other problem. Consider the following heap. If it's a leftist heap, delete max. And if it's a skew heap, delete max. Remember, the difference between a leftist heap and a skew heap is that a leftist heap only cares about, or the leftist heap cares about the null path length, and the skew heap just swaps regardless, right? So that's basically the whole point of this problem. And then what makes them different is that exactly that. So draw a leftist heap that seems right imbalanced, meaning it has more nodes on the right than the left, and the question is, why is it possible? And the answer is, of course, null path lengths. But you have to explain that a little more. You have to tell me what you mean by null path length, right? Null path length is the thing that it's the minimum of the 2 null path lengths of the children plus 1. So not maximum like height, but minimum. So it's the minimum distance to a null pointer. And that's what it has everything to do with, because that's the main property. So there were some questions about, like, if you're going to merge 2 binomial heaps and you have 22 and you have 5, and you merge them together and it's a max heap. So 22 goes up and 5 goes under. Okay. But then you have, like, this here. But, like, the question is, like, what if you had another B1 sitting here too? Which one would you combine? Would you say, I would take the 22 and 5 one and combine it with this one, or would I combine it with this one? Or would I combine these 2 together and leave the 22 and the 5 in the B1 slot? Honestly, the point is, I think normally algorithms will leave the one that's carried in the slot, so the 22 with a 5 under it will be left in the B1 slot if there was something else here so that it would carry. But I don't really care. You can do whatever you want. So that's all I have to say about that. Okay. Yeah, so basically merge them however you feel is right. I think you'll actually have that dilemma when you get up to the B2s, at least for this example, right? Because you're going to merge these and get a B1, merge those 2 B1s, you're going to get a B2, push it into the B2 slot, but now there's 2 other B2s already in the B2 slots. So you have to merge 3 different B2s, meaning one of them becomes the thing that stays, and one of them, or the other 2, become a B3 and move up, right? So that's that. Same thing here. And notice where I put the maximum, right? This is a maximum. Let's consider this a max heap. Hopefully I didn't screw up. It looks like a max heap to me. I was moderately careful to make sure it was stayed a max heap. If if this is the maximum node and you delete it, remember that everything inside of a binomial heap is merge, right? Insert is merge. It's just like a leftist heap and a skew heap. Everything is basically the merge operation. So this problem, right, deleting the maximum out of a binomial heap, deleting the maximum out of a leftist heap, deleting the maximum out of a skew heap, they are all instances of the merge algorithm. So you kill off the 104 and you do the merge, which I will not describe any further because you can check out the other lectures or ask me other questions about it. I'll tell you anything you want to know about it, but that's basically it for that problem. I don't really have too much else to say about it. I hope that everybody... How did you guys feel about it? Was it a good, easy merge problem? You can tell me. Hit me up in the comments. So here, what's the difference between Fibonacci heap insert and binomial heap insert? So remember, a Fibonacci heap inserts by just sticking things into the root list, and it doesn't do any operations on the root list except for it remembers who the maximum is until you do something else, right? And that something else is right down here. So basically, I want you to review the lecture, read a little bit about Fibonacci heaps, and just remind yourself, like, what's the difference between the Fibonacci heap delete max and binomial heap delete max? I'm not going to tell you too much more about that. I feel like you can look that up. And so the whole idea of Fibonacci heaps was that they were basically invented to improve the best case running time for a certain graph algorithm. So they do that moderately well. The actual sad fact about Fibonacci heaps is that they don't perform as well as skew heaps, leftist heaps, even plain old like binary heap, array heap things. So I just went over problem 2, which is probably the thing everybody's interested in. So what's the best case for binary search tree insert in terms of big O analysis? Draw a tree that gives this behavior. So remember that, and I saw this from a few people all the time. Remember that if you have to go to the height of the tree, even if the height of the tree is 1, you don't call that big O of 1, right? Because the height of the tree could be anything. So what's the best case for a binary search tree insert? You have to think about that. Like, what is the best case of it? And, yeah. And then what's the worst case in terms of big O analysis? So you'll have to draw a tree that gives the behavior of the worst case. So basically, you guys kind of know, like, what makes a tree good, right? I mean, the whole point of this class, at least for like a month, was essentially to balance binary search trees. And the reason why we balanced binary search trees is it gave us a certain type of time complexity. It guaranteed that we were not going to get something else, right? Something worse. And then here, what purpose does the successor serve in the deletion algorithm? So what do we do if the successor has a child? So basically what I mean by that is, so remember what the successor is, right? The successor is the smallest node on the right-hand side of the tree that's bigger than the node that we found that we're going to delete. So you go to the tree, you find the node you're going to delete, and then you look to the right, and then, I shouldn't say right. You should look to the right by one movement, and then you look to the left as far as you can, and that is the place where you look for the successor. Now, of course, why do we need the successor in the deletion algorithm? Why can't we just remove the node from the middle of the tree? That's the point of this question. That's what I want you to talk about. So that's the idea there. Tree traversals. Consider the following tree. Good tree. So, of course, the in-order traversal is not very interesting. Because remember, an in-order traversal of a binary search tree is always just the sorted list of the of the numbers, because right, when you go left and then you print out the parent and then you go right, then it's like left, 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 1, print out the parent, 5, print out the parent, 11, print out the parent, 12, go to 12. So 1, 5, 11, 12, 12, that seems fine. Then you print out the parent, 13, 17, 18, 22. Right, this is in order, not something I've asked for, but I'm kind of going through it to hint to you again how to do these kinds of things. I don't know if you needed any help. You probably got through it. But remember, it's a recursive process. All traversals are recursive. So I think that was one problem. I don't know why, but my first 341 class, I was very bad at teaching that. I tried to tell them, but I guess they didn't believe me, or I just didn't say it loud enough, or whatever. So they were trying to do things like, recursing here, and then you would print out this node, and this node, and then you would print out this node and this node and this node, and then you print out this node and this node. Like, you would actually go down and print out all 3 of them at each stage. But remember that these are recursive functions, so the in-order traversal function starts here. It calls the in-order traversal on the left, and then so basically it prints out everything here, and then it has a print statement, and then it calls in-order traversal on the right node, which then does the same kind of process here. So that's the point. And so basically a pre-order and a post-order traversal are exactly what they sound like, right? A pre-order traversal just means that before you traverse any node, you have to traverse both its left and its right child. And by saying its left and its right child, I don't just mean the left and the right child. I mean the entire subtree that the left and right child are parents of, or are the subroot of, or I think that's technically correct, is if I say, like, the subroot of that subtree. Okay, I like this one. It's almost the identical problem that I went over for the practice final on the last one. So the only thing I did, so just make sure you realize that I actually did flip the colors. I basically left the example almost identical. I just flipped the colors. And so your first question is, should this even be possible, right? If I flipped like a red into the root, or I messed up something somehow, it's possible that there's no red-black tree like this, but of course there is, right? So you just have to figure out, you know something about the root, you know something about this node a little bit, and then you know the black height, and then you can determine the black height over here, and so then you know how many black nodes you need on, each position, and you'll just have to go through, you'll go through that and you'll try to understand that as best you can, right? Use the rules and fill in the tree. I think that's as much as I want to say about this problem, mainly because I think red-black trees themselves are mega hard, but I think this problem in particular is not hard. So I could be wrong. I'm wrong about a lot of stuff, but I don't think this problem is terribly difficult. So I will simply say good luck, and remember the red-black rules. And if you don't remember the red-black rules, pull them up, because they are on websites like Wikipedia, or on better websites or for coding or whatever, or in your textbook if you really want to open a textbook. I mean, that's up to you. So let's do a depth first search. Let me show you an example of a depth first search, but let's do it from a different node to a different node so that it's not the same process that you'll have to do on your exam. So let's do, as soon as I find the mouse is like flittering around. There it is. There it is. Got it. Okay. Okay. Cool. And now for our feature presentation, we want to go to this one, I guess, and just blurb it in. So let's do a depth first search and a breadth first search of this graph. But let's make sure that we start at different nodes and end at different nodes so that it's all, so that it's different. I guess that's what to say, right? We want it to be different. So basically, let's start at H and try to get to D, right? So this is the path that we're going to take from H to D, right? So we start at H and we go to D. Okay, so we can live with that. That's a fine path. And we're going to do this in a depth-first way. So depth first, what does that mean? Right? That means that you're using a stack to control the program, or which node you visit next. So the first node you're going to put on is H, right? And then you say, well, wait a second. H isn't what I'm looking for. So I pull that off. So I already pulled that off the stack. But then I put onto the stack. I guess I can put on A, and then there's also B and E. So we have A, B, E, L, and N. And I know I'm just drawing letters right now, but let's just... So then we put them all in the stack, so let's do that. Come on. Come to me, little stack node thing. Okay, almost there. And now what happens, right? So this is how I was drawing it before. So now N is at the top of the stack. And so what we do is we say, okay, let's pull N off the stack. And then what we're going to do is, remember, you can't add the H back because that's where you came from, but you can add M and P. So we're going to add M and P. And remember, this is a stack, so the one thing I'm not going to specify, and I didn't specify, is the push-pop order. I didn't say that you had to do it in alphabetical order. You can decide the order that you push or pop the nodes on, but one way or the other, you're going to either get MP or PM, and that's going to be it, right? Because those are the nodes. And so let us then pull off M, right? And I'm putting M down on this list of visited nodes, right? So M gets pulled off, but we don't get to put N back on because we've already visited there. So M dies, so then we pull off P. P has one child, which is T, so we put T on the stack. Well, I shouldn't say it has one, it has two, but one of them is backwards, so we don't go there. So then we pop off T off the stack, and then we say, okay, well then there's Q, right? And then we pop off Q off the stack, and then there's R, right? And so what node are we looking for? We're looking for D, so we're never going to get there. So now we're going to pop off R off the stack and look for S. Going to pop off S off the stack, and then finally we have more than one choice. We have K and L. So the question is whether or not we put K, L back onto the stack, right? Because L is already on the stack. Let's say that we don't in this case. We only put it on the stack once. So then we shove K on the stack. So then we pull K off the stack. And we put on what? H, which is the starter node, so we never put that back on. F, which is the next node. Wow, and then here we say, okay, pull off F, we put on G, and then finally, well, I guess that should be capital G, and then finally, you pull off G, and you put on D. I think you also put on E, maybe, but E's already on the stack, so really you just put on D. And then when you pull D off the stack, your path is finished. So if you look at your path, you start at H, you go to N, M, technically back to N again, and then you go to P, T, Q, R, S, K, F, and then F, G, and then D. So F, G, and then D. And so the answer to that is that what does depth first search do for us, right? DFS is a stack-based search, which means it's going to run faster probably, but it's also going to find kind of windy, non-optimal solutions. And so basically, let's try to do this again, except let's do breadth first search. Same nodes, everything's the same. And you see that I used the same stack now. If you actually write this out, what I think is probably a smart idea is that you use the stack for a while for a few of the inserts and deletes and you cross things out. And then what you can do is when it gets messy enough on one version of the stack, then you just copy it over to a fresh stack and show me how things have evolved, right? So for instance, like, so yeah, let's see how breadth first search handles this thing. So this was a stack. Yeah, so intermediate steps, by intermediate steps what I mean is like something like this. You would have like 3 of these or so maybe, and some of them would have like H, M, and N and all that stuff, and then like the rest of them would be in some other, something like this. For depth first search, I don't know what the numbers are actually. I'd have to do it out myself. And of course here I definitely picked a kind of windy way to do it. So remember, if you picked luckily, if you'd say, oh, when I pull off H, I put on G, or I'm sorry, if I pull out H, I put on E, pull out H, I put a G, then you're there in 2 steps, right? So depth first search can find the path in 2 steps, but it can also find the path in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 steps. So the question is that the real question that happens when you're doing a depth first search or breadth first search is what order do you put on all the adjacent nodes, right? Like generally, technically, if they're not labeled with an alphabetical order or anything like that, how would you know whether to put on P first or Q first? And the answer is, well, here, you go elemental P, Q, R, S, so I guess P comes before Q, so you put on P first. But it doesn't, there's nothing that says that computer science-wise. So, yep, okay, so let's do the breadth first search. So let's draw ourselves a queue now. And let's copy the graph and our destination. So we're going to start off at H and go to D again. But this time we're going to use a queue which is breadth first search. And yeah, so just remember in your future life that Dijkstra is kind of a modified breadth first search with it's a modified breadth first search with weights. Okay, now that I'm here and thinking, so we're going to push on H onto the Q, right? But H is kind of like goes to the front of the line because there's nothing else in the line. And I guess we'll say it DQs, right? So H DQs. But what does it push on? So it does basically the same thing that the other one does. It's going to push on, I guess, N, L, N, L, E, A, B. So E, B, and A, right? So this is going to get pushed on. I guess we're doing it kind of in like reverse alphabetical order, so we could do it in alphabetical order, but it doesn't matter what order you actually do it in. It just matters that you pick some random order, and at least at that node, you know whose node gets added to the queue first. So then what we do is we DQ this one, and we see what kind of changes go on. So we dqn, so then we nq, right, m and p, just like we did before, right? And then we dql, and we nq s and k, so I'll do s, k. So this one's going to have a lot of stuff in the search, right? Because now we dq e, and E puts on, what, C and G, but it's going to put them on like this, so it'll put them on G and, oops, and C, like that. And then finally, well, I shouldn't say finally, because we're nowhere close to done. Finally, I move the stuff to the front. So this would be a good opportunity. Like once you have some stuff crossed out in your queue, you could always make a copy of the queue and just copy the new letters over and push them up. So then you have room in the back of your queue to add more stuff. So then we pull out B, and B adds F. And then, let's see, F and G. Oh, right, but G's already been added to the stack, so, or added to the queue, so we're okay. Okay, so then we pull off A, and then A goes to D, and G, which has already been added, so there we go. And then we pull off, and so the thing is, sometimes the depth first search algorithm detects that it's going to the right destination and stops here, and sometimes what it'll probably do, at least your first implementation, may actually just keep dequeuing until it finds that node, not as one of the neighbors, but actually, actually dequeues it. So here, we pull off the M, but you remember that the N is already on the stack, so or already in the queue, so it's not gonna do N again. And then here we pull off P. Okay. Yeah, so we pull off P and we put on T. And we just have to keep doing this until we get to our destination, right? So we're going to say pull off S and put on, what is it, L and K. But K's already on there, so we don't do it again. Okay, so then you pull off K and put on F. F is already on there, so we're good. Pull off G. Try to put on E, B, F, D, and A, all of which have been on before, so we don't do anything. And then we pull off C, which is a dead end, so it's not going to add anything. And then we pull off F. Oops. We pull off F. Now this is actually not the path, right? So the path is a little more complicated. You have to, basically each node has to remember which node it came from in order to make the shortest path. So what is the shortest path? Basically, now you pull off D, but then we have to remember where D came from. D probably came, I think D came from A, right? Well, firstly, that's the shortest path. So it had to have come from A. So basically the shortest path will take us from H to A, D, and that's it. And you have L and T left in the stack, and maybe some other stuff that I didn't add. So basically this is what I want. I just want like a list of nodes that you've searched, and I want like the path in the end. So I basically want you to say like H to A to D, and that's it. So if there's multiple short paths in the graph, it's completely fine if you have any particular short path. There's no preference, as long as it is a shortest path. Okay, let's look back at the questions. This one. The only thing I really want to say about this one is that you do have to use the shift back method. And the other thing to say is that let us, again, use Windows Calculator to verify that all of these numbers are in fact correct. So 19 mod 6, even though I should know that, 19 mod 6 is 1. So that number should be in this slot, so that's correct. When I wrote the test question last year and then I forgot what I did wrong, I accidentally made 6 slots rather than 5, and then I made the hash function x mod 5, which is because I thought there were 5 slots instead of 6, and so so there are 6 slots. So 14 is 2 mod 6. I guess that makes sense because 14 is 12 plus 2. 31 is 6 times 5, so that's really 0 in the mod 6 system. So it's 0 plus 1, so it's 1 mod 6. So actually this is in the wrong place. So how did this thing get into this place? Like, what happened to put it here? And the answer is, well, it collided with the 19, and then it tried to go here, and then it tried to go here. Excuse me. So that's the point, is that this was a hash collision, right? So the 31 is a hash collision. 43 mod 6 is also 1. I think I made them all 1 except for 14. 14 is the exception. Yeah, that one snuck up on me. So 43 mod 6 is 1. And that's true because 6 times 7 is 42, plus 1 is 43, so that is yet more confirmation that this is in fact 43. Or, I'm sorry, 1 mod 6. And so basically the point is that here, you're going to shift this one back 2, and then 25, let's see, 25 mod 6. Well, we don't even need to do that because 24 is 0 mod 6, 25 is 1 mod 6, which it is. So basically, the whole point of me talking about this problem is not to really tell you how to do it. I'm just reminding you that this one, not this one, but this one, that one, are all 1 mod 6. So basically everything but 14 is 1 mod 6. And then what was your favorite data structure and why? I think it has to go to binomial heaps. And the reason is because they give really cool little combinatorial formulas. And I think that's adorable. So adorable, in fact, that I made it another test question. So that's what I would put here. You can put whatever your favorite data structure is, but I say binomial heaps. At least for today, that's my favorite data structure. Maybe tomorrow I'll decide something different, but okay. All right. Are there any other questions about the exam so far? I think I've gone over everything I really wanted to say about it. I think I've said quite a bit about this stupid thing. Hopefully everybody's either finished or getting close or whatever. Do a BFS. Oh, look at that. I gave you plenty of room here. Literally 0 room. I should have put this on the next page. Okay. Yeah, so I would say just like follow through what I was saying about number 2. And then try to generalize it, because I was basically going like 5 choose 2 plus 5 choose 3 is 6 choose 3 or whatever. Whereas you should really be saying n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. Yep. Okay, and then I did a little bit of induction at the beginning, so if anyone's interested, I actually did the square case. Number 2, well, no, look, number 2 is going to be whatever it is. So I'm going to deal with number 2, and if no one gets it, even vaguely reasonably, then I don't know what. Like, don't worry about it. Just do your best on number 2. Tell me something reasonable. Try not to... Make sure that more than helping me to understand number 2, try to help yourself understand number 2. Try to get it to the point where you kind of understand what it's supposed to prove. And just kind of, even if you don't feel like your proof is perfect, like explain what you're trying to do. You know, use some words and try to kind of verbosely tell me how you're attacking the problem, and then I'll give you some partial credit or something. So I wouldn't worry too much about number 2. All right. well, I guess that's the actual end of 341. Hopefully everyone vaguely enjoyed data structures to some extent, and hopefully you'll take your knowledge and do well in algorithms and, use your knowledge in future classes and coding interviews and stuff like that. So, yeah. So this exam is technically due tomorrow at midnight, and that's when I'll start grading. I haven't touched any of it yet. If you submitted, I haven't looked at them until all of them are submitted. If you want to talk to me about projects, I know that some people do. We should definitely do that. I'll be around tomorrow. I'll be around. Well, I won't be around Thursday. I will be in here on Thursday, but I'm not going to be available for horrible and stupid reasons involving lots of 201 students who did naughty things. So, yeah, so basically either tomorrow or maybe Friday we'll talk about, or maybe even today, we'll talk about any projects. So basically just tell me what time you guys are available, and I'll be around, and we'll pull up your projects. And I can't promise you that I'll know everything about every little detail of how things were run or graded, because as it turns out, I don't really know. They don't show me all the tests, so it'd be nice. Okay, I'll let you go. I'll let everybody go. Have a good rest of your day. All right. Bye. Bye-bye. Outro for the last time, at least in this class. But, don't get help. Don't get help. Class is over. There's no more help. Goodbye.